Yeah, good morning, everybody. Welcome to our multi-cluster Kubernetes meeting of the CIS Workstream 2. I took over you might be surprised that I'm presenting today, that I start the meeting. I took over the organization of that meeting from Vasu, and I will also organize that meeting then in future. We opened up this series now to the NeoNephos Foundation. So also welcome to guests that haven't participated before. One important thing as a consequence that we opened up this meeting series, we are only allowed to present topics that are not IPCEI internal. We never did so before. So I guess there should not be any change to the agenda that we had in the meeting so far, but just as an information. If we have IPCEI internal topics, we should discuss them in the respective meetings of the respective internal meetings of the IPCEI organization. Because we also have the NeoNephos Foundation, we show here the antitrust policy. That's also very important to consider. And yeah, so our agenda for today, we first have a talk about the Gartner autonomous shoots clusters by Raphael and Dominic. And then we have an introduction to sustainability and smart energy workload placement by Keith from Telecom. Okay, with that, I would like to hand over to Dominic. Dominic, just take over the presentation.
All right, then let me share. And starting presenting mode. Maybe just a second, get rid of this one. All right. This way. Okay. All right. Thank you. Thank you very much. Thanks for having us. My name is Dominic Kistner. I'm from the SAP Gartner team. I'm together with my colleague Raphael Franzke today. Give you an introduction in Project Gartner, or in more detail about the work stream, which is that we call autonomous shoot clusters. But before we dive into that, I would like to recap a little bit on the IPCEI. Actually, the IPCEI, as you probably know, aims to build a sovereign, secure and interoperable European multi-provider cloud edge continuum. It's for me always a little bit a heavy term to pronounce. So in essence, it is an initiative to create an overarching continuum, which is open for any kind of infrastructure, platform, or service provider to integrate, and which is spanning over from cloud environments or onto the edge. With the Apiro reference architecture, SAP is contributing to this initiative. So Apiro is SAP's ongoing project for the IPCEI. Within Apiro, SAP is bringing in or contributing some key building blocks, such as infrastructure provider blueprints like the Iron Core project, the Cobalt Core project, a bare metal automation layer, which helps you to automate data center resources, a platform mesh, which makes it easy for service providers to integrate their offerings, a bunch of operational and security services, and a multi-provider managed Kubernetes offering, and many, many more. We all combine that in Apiro with an overarching concept to build a holistic stack, reaching from the data center on the bottom up to the software as a service layer on the top. So within Apiro, we proclaim a so-called operating system, a cloud operating system, which we use to build a higher level services on it. So the cloud operating system actually at all is not a single service. It's a bunch of central services that you require to build applications, like it's an identity provider, identity and account management, identity and account management, an IIS provider, and that can all be leveraged to build higher level services on top. One of the design principles that we apply in Apiro is that we don't use individual individual machines anymore as the base unit, so to say. We are building everything on top of clusters where we can run containerized application and services on. So in essence, Kubernetes. And as you can imagine, for such an endeavor, building up such a stack, you require a lot of Kubernetes. You require it in a homogeneous way. You require it across different providers. So it's not feasible to go with individual handcrafted Kubernetes clusters. You need instead a managed Kubernetes offering which can offer you the things. And that is where Gardener comes in. So Gardener, the Gardener project offers you fully managed Kubernetes homogeneously across all different providers. What does it actually mean? It is independent where Gardener brings your cluster or where you bring a cluster with Gardener, you have the same kind of capabilities and management options. So you get the same configuration options for your Kubernetes clusters, the same Kubernetes versions you can select. You can also and manage all of your clusters or your fleet of clusters from one central point or out of one central service, which makes it, of course, very easy to manage a lot of clusters, as we said, that we need for building such a stack. Gardener also comes with a extension concept, which makes it super easy to plug in any kind of infrastructure that you want and run a cluster on it. So be it on a hyperscaler or in your private data center, or even on the edge with Gardener, that's easily possible and to achieve. Now I want to dive with you a little bit into the Gardener architecture. So for that, I wanted to start in the right. There you see the term shoot cluster. And the shoot cluster actually in Gardener, in Gardener is actually an end user Kubernetes cluster. That's the cluster where you can run your application, your containerized applications in. And Gardener is leveraging the hosted control plane or kubeception model, which means we are hosting the control plane of a shoot cluster within another Kubernetes cluster that we call the seed cluster. And of course, in one seed cluster, we can not only host one control plane, we can host there many. And we also have in Gardener a central management plane or control plane where you can specify your clusters or can do where you can manage actually your clusters. We have on each seed a central Gardener agent that we call the Gardenlet. It's very similar like to Kubernetes, where you have the kubelet running on each machine, which is responsible for managing the containers on the seed or the pods and the containers within on a worker node. We have in Gardener on each seed a Gardenlet running, which is responsible for locally managing the control planes and the clusters on this hosted on this seed cluster. You as an end user, you are talking to the central Garden API, and you specify there your cluster. So you do it completely declaratively with you specify a Kubernetes cluster with a Kubernetes as a Kubernetes custom resource, and then it will be picked up. It will be scheduled to a seed cluster, and then the Gardenlet on that cluster will take care to create the cluster, and of course also taking care about all the lifecycle operations on the seed for the shoot cluster. And as said, you cannot only have that's way what it looks like. So you have here a shoot manifest. In this example here, you have a shoot cluster that I call my shoot. And I want to have it here. I declare I want to have it running on Kubernetes 1.30, and I want to have it on provider OpenStack. That's of course just a very minimal example of a shoot manifest. You can have much more details, but for instance, you can completely customize the control plane and all of that of the Kubernetes cluster, and you can do it on whatever on any kind of provider which is available to the Gardener system. Which means you can also bring additional seed clusters to plug in additional cloud providers or regions. It's just and of course host then there the respective end user cluster shoot clusters for your end users or for the Gardener end users. All right, and with having that introduction, what most important to recall, shoot cluster is an end user cluster we hosted on a seed. The Garden cluster is the central unit or the service layer where we actually configure your cluster centrally, or where you can configure your cluster centrally, and they get then managed by the Gardenlet onto the different seeds. Now I want to look with you a little bit on the cloud edge landscape, because where we position Gardener therein. And you see here, for instance, Gardener is with the working quite well in cloud environments or in, let's say, regional data centers that usually have consistent network connectivity, or where you usually have consistent network connectivity, where you have APIs to automate things, where you, for instance, can request virtual machines or network resources or storage or whatever else, where you have failure domains, which means, for instance, you have a concept where how to distribute your workloads, like availability zones, and making sure that they are run in a failure tolerant mode. And in this way, the hosted control plane model of Gardener works very, very well. But in the IPCEI, we want to go even further on the left in this on this landscape. So we want to reach into the edge, and there we have usually the problems that network connectivity is not always given. Or that you don't have APIs to automate things, you don't have failure domains and all of that stuff. So just assume you have a cluster running, I don't know, in a factory somewhere in the back, in a factory, or you have it somewhere in the office running, or even on a ship, an airplane, whatever. And many cases are possible for an edge scenario. So therefore, we are introducing in Gardener a new concept or a new kind of clusters that we call autonomous clusters, or to be in our terms, autonomous schools. And they will help with these kind of scenarios. Let's look at, let me introduce that a little bit to you, what it actually is. So an autonomous cluster actually consists out of some worker nodes, obviously, and control plane nodes, where we host a control plane. So you may ask, in essence, that's like a traditional Kubernetes cluster that you also get if you craft it by hand, or if you use tools like kubeadm, K3s, whatever else. But the difference that we're making is we are putting also the Gardenlet and some other Gardener-specific components that I didn't depict here, and connect the cluster to the Gardenlet, to the Garden cluster, so that we can consistently manage it centrally from the central service layer of Gardener, so that that you can control your entire fleet of clusters from one central point. That means if you have registered it, you get for the autonomous clusters also in the Garden cluster a central representation, and you can continue to manage it from there on. I want to look with you a little bit also on network boundaries or isolation domains and why they matter for the case, and especially for the edge. For that, I brought in here also another figure of a, let's say, traditional or regular shoot cluster. And here you see the worker nodes and the control plane nodes, they are running in different domains. So you have usually the shoot cluster worker nodes running in one network domain, which is usually controlled by and owned by the owner of the cluster, so to say, or the end user of the cluster. You have the seed cluster usually running in a different networking domain, usually owned by the operator of the Gardener service. You have the Garden cluster running in a different network domain. But for the autonomous clusters, we package both together within the same network domain. And this has the big advantage that the network connectivity between these two things is always will be always stable or more stable. They are in the same networking domain, which means if you think about running on the edge, if you, for instance, my example is always having here, I have a seed cluster running in a harbor, and I have a shoot cluster running on a ship. So probably the ship doesn't have network connectivity all the time to the harbor. So in this case, you would have a problem with the traditional approach, because the cluster, actually the shoot cluster, is not functional if the control plane is not available. Therefore, we package them together, and we also want to provide options that you can temporarily disable it without having any issues. So we still want to provide air gap capabilities so that you can run the cluster or air gap the cluster for a while and make some modifications in the central Gardener. And once the cluster is available again and can connect back to the Garden cluster, it will fetch, or the Gardenlet will fetch the details and will run or will then do the lifecycle operation. That could be, for instance, I say I want to upgrade all my Kubernetes cluster from 1.30 to 1.31, and only once the autonomous clusters can reach the Garden cluster, the Gardenlet will get this kind of information and will run then the lifecycle operation. So with autonomous shoots, we also have defined, let's say, a few different scenarios that we want to cover. Actually, we have one scenario that we call the unmanaged infrastructure scenario, and we have another one that we call the managed infrastructure scenario. I want to start on the left with the unmanaged scenario. That's actually the scenario where you only have, let's say, a bunch of pre-built servers, so you don't have any kind of automation layer to request machines. You just have a pre-built setup of machines which are connected via networking, but there's no mean to automate anything here. So you cannot request a virtual machine or something like that because you simply don't have an API for it. Then you have the case which we call the managed infrastructure case. That means there are APIs to certain things, so you can certain things automate, like compute, storage resources, and maybe also networking. And in this case, we can leverage existing Gardener and Kubernetes platform integrations to automate things for building up an autonomous shoot cluster. So in this scenario, we have either a complete automation layer, or we have just a partial automation layer. So it's thinkable that you can maybe automate or request virtual machines because you maybe have something like a vCenter or so, but you don't have network. So that means hybrid scenarios in between are possible that we can use, or that you can are thinkable. And then I want to go to this picture here because it's very important and shows the architecture of Gardener, or the key principle. We have the central Gardener in the middle as one central platform to manage all your clusters in the same way, independent where they're running. If they're running on the with a hosted control plane mode, so the traditional mode or the regular mode of Gardener, with seed and shoot clusters, usually fitting quite well for the cloud, you manage them in exactly the same way like you do it for autonomous clusters who might running in a factory or wherever else, where you don't have capabilities to automate things and where network is maybe separated. So these clusters, they're running within the central Gardener side by side, doesn't matter, and managed in the same way like regular shoots side by side. Okay. Now you might ask, okay, how do I build up such an autonomous shoot? Set with Gardener, with the central approach, you usually just go to the central garden, you specify a custom resource, a shoot custom resource, define there how your cluster should look like, you post it there, and then the Gardener will take care to create your cluster. But how are we doing it in case there is no automation layer, so nothing Gardener can leverage? For this case, we invented actually a new command line tool that we call the Garden ADM, which helps us to bootstrap autonomous clusters. It is actually using the same configurations that we are using also for regular shoot clusters. So it's not like kubeadm, which might come to your where you think of. kubeadm and other tools, they are following a rather imperative approach. Garden ADM is using a declarative approach to define the clusters and managing it. And then, of course, it also helps us to connect this garden to connect this cluster later on to a central garden. And now I want to give you an example of for an unmanaged infrastructure scenario, how to build up a cluster with Garden ADM. And for that, you are here in the middle, you are the operator, and you want to build a Kubernetes cluster. What you actually have is a bunch of servers. They're called A, B, C, D, and E, and they are connected via network, so they can reach each other. So what you first would do is, you have, of course, the Garden ADM tool. The first thing what you usually could do is you could try to discover an existing Gardener and to get some configuration, because to build up the shoot cluster, you need some kind of information, like about the environment that the cluster should be running in. We call this in Gardener cloud profile, or the kind of extensions or the additional functionality you want to have on the clusters. These kind of configuration you could get from the central garden if it is available. You can get it there, and with the Garden ADM discover command, you will get them and fetch these kind of configuration for the cluster that you want to build up. In case it is not available, then you need to provide it manually, but it's not an issue. You can do it, but it's of course more handy if you have it. And then we will start to create a cluster. So what we will do is we will jump on the first machine, we will run the Garden ADM init command, and with that, we make out of these 5 servers, out of the first one actually, we make it to a control plane node, and we put a control plane on top of it. And then what we probably want to do next is we want to join a few more control plane nodes, maybe 2 others, so that we can make the control plane with an etcd cluster highly available. And for that, we are generating a bootstrap token, and then we jump on the different machines and we run Garden ADM join. And then the other servers B and C will join A and will be registered as a control plane node in the cluster. Next, you probably want to have some worker nodes where you can run then or where you can then deploy some workload on. And for that, you can run again the Garden ADM join command, or first you run the token command to generate a bootstrap token again, and then you join the other 2 worker nodes to the cluster, the other 2 nodes as worker nodes to the cluster, and then you have it. And at this stage, you have a fully functional Kubernetes cluster. You can do whatever you want with it, but it's somehow unmanaged. It is there. And now comes the trick, actually. We want to connect the cluster now back to a central gardener. And for that, we have the Garden ADM connect command. And with that, we install the gardenlet onto the seat, onto the one of the control plane nodes. And it will then call back to the central garden cluster and registers actually this cluster as a shoot cluster within the central gardener environment. And from there on, you can talk to the central gardener and you can modify your shoot manifest. For instance, you can say, hey, now I want to trigger upgrade the Kubernetes version of this thing. And then the operation will be done, handled by the gardenlet in place in the cluster. And that is what we want to show you now with a demo. And for that, I hand over to Raphael.
Great. Thanks, Dominic. And also hello from my side. Let me share my screen. And with that, we can get started with the demo. So actually, we are here in the kind of unmanaged infra scenario. We simulate this with a kind cluster on my machine. So what I've basically set up is just a very basic 1 node kind cluster, not any special configuration whatsoever. And here we have a namespace for Garden ADM where we have 2 pods, machine 0 and machine 1. And let's say these pods are simulating your nodes in the edge. So those are basically just like VMs or machines that have an operating system. They are booted, but there's nothing installed in them. And you can now exec into them or SSH into them and run commands. And this is what we will basically do now. So here we have exec into the machine. And we will now first look into the configuration that we have provided to it. And Dominic actually explained with the Garden ADM discover command is that you need some configuration of how the cluster should look like in the end. So you have here, for example, the registration of an extension called provider local, which runs in some version. There are some other extensions registered here for networking, the Calico and the Cilium extension, and so on. It's not so much important. If you are familiar with Garden, you might recognize most of them. The most relevant resources at the top, which is the shoot manifest, the declarative cluster specification. And if you know it, it looks quite similar to the regular shoots with the seed architecture. There's one difference here, which is that you have a worker pool that is marked as control plane worker pool, meaning that the control plane components are now supposed to be self-hosted and running in this cluster instead of running in a seed. So that's basically it. You have a file or many files, basically a folder where all this resides. And this you can now use in order to run Garden ADM init. You just point it to the directory where the configuration is stored. And then this runs. For the sake of time, I have already pre-executed it because it takes some minutes until all this gets up. But in the end, as explained in the slides, you will now make this node, Kubernetes node, in the first control plane machine, basically. So let's have a look on it. It should be ready in a minute. Yes. So now it's done. It tells us that the control plane has been initialized successfully. We get some information on how we can now talk to the cluster, where the kube config resides. We will do it in a minute. We also get some information how we can now join additional nodes to this cluster. And finally, the most important thing, how to connect this cluster to Gardener eventually. So let's start with looking what we have created here. There's one node in the cluster called machine 0. And the pods in the kube system namespace are not too special. They are typical system components like kube proxy, Calico, CNI, core DNS, and so on. And of course, also the control plane components of this cluster running as static pods. So we have etcd, API server, and so on, the usual suspects. And if you are familiar with Gardener, you notice that we are basically reusing existing functionality that we have already built. So etcd Druid, which is our etcd operator, managing etcd clusters, is used here as well in order to bootstrap the etcd nodes. Then we also have our Gardener extensions running here. So in this case, provider local because we're in this local kind environment, but this could also be if you have a managed infrastructure, AWS or whatever else. And of course, the networking extension. This is all here in the cluster and basically self-contained. So now you have a ready cluster. You also have a backup bucket here for the etcd of the cluster. So the data is backed up in the local environment. This is more or less a host directory mapped from my machine into this container setup. So we could check it out here in this local backup buckets folder. There is this name F5E, which corresponds to the name of the backup bucket here. And if we take a look what is inside, then we find there's a full snapshot and every 5 minutes an incremental snapshot. So the usual backup and restore functionality that we already have. All right, and now with that, you can basically start deploying workload and use the cluster, whatever you want to do with it. What you eventually probably need to do if you deploy more and more into it is joining additional nodes and scaling the cluster. And this is what we will do next. For that, as shown in the slide, there is a command called token used for managing bootstrap tokens that then can be used for Garden ADM join or also later for connect. So if you are familiar with kubeadm, this should not be much different to you. There is a Garden ADM token create, and you can tell it to directly print the join command for this created bootstrap token. So this is the token that we got. There's a big CIS certificate in here. There's a flag pointing to the configuration for the node that is to be joined. So this contains like the kubelet config and so on. And finally, the address of the control plane where the to be joined node needs to talk to. And yeah, executing this list again, we see that this bootstrap token is this one here. It has a default expiration of an hour. And yeah, eventually gets also deleted when it expires, but you can also delete it yourself if you want to. So let's go to machine 1 and let's watch the nodes here to see what happens when we execute this command. We basically just copy paste it. It tells us that this node has been instructed to join the cluster as a worker node. And this is what we expect to see here now. Machine 1 is coming up. It's not ready because all the system components have to be initialized. But this will happen eventually, and then the node will also be marked as ready. So note that the worker node, it's not a control plane node. But for control plane nodes, the command and the flows should actually look similar. All right, so as said, you can, if you want to, delete the token that you just used manually in order to invalidate it, or you just wait until it is expired and garbage collected. So now that we can deploy workload and add nodes, we still need this day 2 and life cycle for the cluster as such, as Dominic already explained. And for this, we, of course, want to use the same declarative approach with Gardener that we also use for clusters that we run on cloud, for example. In order to demonstrate that, we go back to the kind cluster. In the Garden namespace, I have prepared Gardener deployment. So with the help of this Gardener operator here, we see that we have the Gardener API server and the other Gardener components that belong to its control plane. There's also this Garden custom resource that depicts that there is a Gardener instance here. And we can now talk to it and list the seeds. There are no seeds at all because I didn't install any. They are not needed for this demo. Just want to show you that there is an empty Gardener that we can now use to talk to and connect this autonomous cluster. Again, in order to connect it, we need some kind of authorization and authentication. We create a bootstrap token. There are none currently. So similar to how this works for the join, we can also let it directly print the connect command. Here we also have to tell it which shoot namespace and which shoot name this token should be related to, because we don't want it to be used for other things other than registering exactly this shoot. And then this command actually looks very similar to what we saw before. Garden ADM connect, some bootstrap token, now the CA certificate of the Gardener and the address of the Gardener API. If we list them again, we can see in the description that this is a token that is used for connecting exactly this shoot that we specified via the Garden ADM connect command. All right, so otherwise, same workflow. We copy this, we go onto the machine, paste it here. We start watching the shoots, execute it and see what happens. The shoot manifest now gets registered in the Gardener. And we see that this command is still running, now deploying a gardenlet into this autonomous cluster, which is then just like it's also doing it for seeds and shoots. It's watching this manifest and reconciling it every now and then, making sure that the specified state is also the actual state in the cluster. So if we check the pods, there is now a deployment of Gardenlet. And what we can do now is, as before, or as we are used to basically with clusters in the cloud, edit the shoot declaratively, change whatever we like, whatever setting. Maybe this we want to increase, save it, and then the Gardenlet here will make sure that it is rolled out. Another thing that you might wonder is how this Gardenlet here is now kept up to date, because sometimes we have new versions. You want to roll this out to the autonomous clusters in the edge. And for this, we have a resource called also Gardenlet in the Gardener API. This usually represents a deployment of a Gardenlet in a seed, but it can now also represent a deployment of a Gardenlet in an autonomous cluster. So let's take a look. For example, what can you do here? There is the image specification of the Gardenlet repository and the version. So if there's a new Gardener version, you could, for example, just dump it here and it then gets updated. You can also modify deployment configuration like CPU memory requests, or you can modify whatever else is Gardenlet specific. So it's configuration. If you want to change something here, you can also do it. For the demonstration, we just make a simple change here and increase the memory requests. We watch again the Gardenlet pods. And when I now save this resource, the Gardenlet immediately starts to roll out. So it's basically self-upgrading. It's watching this resource and redeploying itself with the new configuration and maybe in a new version, if there would be a new version. All right. And what else do we have? If you check the help command of the Garden ADM, besides the things that you already saw, Discover I didn't show you, but it's also just the convenience method for downloading the configuration. Another important command is this bootstrap command. So this is useful when you have a managed infrastructure, where you have an API that you can use to, as Dominic said, create machines, create networks, create storage, whatever. Let's say AWS or whatnot, so some kind of cloud provider API. If you have that, then you can use the Garden ADM Bootstrap in order to let Gardener prepare your infrastructure, meaning it might create a VPC and subnets and use the machine controller to create VMs and prepare all this what you basically need to do manually in an unmanaged infrastructure scenario on the edge. So this means that you can use autonomous shoot clusters also for cloud environments if you have special requirements. Most importantly, you can use them to bootstrap Gardener itself, because somehow you need some Kubernetes cluster in the beginning in order to deploy Gardener to. And this is also a goal actually for the autonomous shoots. If you want to learn more about this command, because we don't have the time to show it here, we coincidentally have a presentation about it in tomorrow's Gardener review meeting, which happens bi-weekly on Wednesdays from 9 to 10. I will post the link in the chat. If you would like to join, just reach out, and then you could also see a demo for this scenario. And with that, I will hand back to Dominic.
Thank you, Raphael. Awesome. So, yeah, okay. Going back to wrap it up, I would like to give you also a little bit an overview about our plans and the upcoming milestones for autonomous clusters in Garden ADM. So, as Raphael mentioned, one of the goals for autonomous clusters is also to solve the so-called first cluster challenge. So you might ask, what is that actually? Actually, our first wave is part of the Garden enhancement proposal that we wrote for autonomous clusters, GAP 28. And what actually is the first cluster challenge? For that, I want to go back a little bit to the beginning, where we talked about the Apiro stack and said everything is built on top of Kubernetes. And you just see in the beginning of the layer, Kubernetes is somewhere in the middle of the stack and way below under Gardener. So, and as we learned, Gardener is also requiring Kubernetes to be set up, same like for the infrastructure provider blueprints that we offer and the bare metal automation. So we need actually for all of that Kubernetes. And after the session, you probably know where this should come from. Of course, it is an autonomous, or should be an autonomous shoot cluster that we build with Garden ADM init and join. And once we have done this, we can deploy these kind of applications on or the services on top of this autonomous shoot clusters or the autonomous shoots. And once the Gardener is then up and running, we can also connect it via Garden ADM and close with that actually the circle. So it's a little bit like that here, like the Baron Münchhausen, who's trying to hoist himself out of the swamp. So we are also trying to pull out ourselves with the burden of managing Kubernetes in the very beginning, where you don't have anything. We are doing that completely closed within our ecosystem, the same means that we have for any other kind of cluster in Apiro. So, and that beyond that, actually, we want then in the second wave to enable also our end users to connect autonomous shoot clusters to the Garden, which means that we enable edge use cases for end users. But for that, we have certain things that we need to work on, and that will be handled in a follow-up Garden enhancement proposal. There will be questions open like, yeah, how can the air gap handled? How long, for instance, can a cluster be air gapped? These kind of questions need to be clarified. But we also have a lot of technical questions that we need to solve. So, for instance, the Gardenlet is a component designed to run on a seed. So in the operator space of Gardener, so to say, with autonomous clusters, they are now coming into the user domain. So there's probably some questions open for access control, but also with respect to scalability and VPN and many more. Yeah, with that, I would like to wrap it up. Thank you very much for your attention. And I think we have some time left for Q&A. In case you have some questions, please go on.
I think there's one question in the chat from Valentin about turning back an autonomous managed cluster into an unmanaged one. Actually, there are two questions. Okay, but turning back the cluster into an unmanaged one is possible by deleting the tree from the Gardener and then removing the Gardener deployment from the cluster. But yeah, I don't know why this could ever be needed, because with that you would lose the lifecycle operations and cannot further maintain the cluster. So I'm not sure why this would ever be done by somebody. As for deletion of the cluster, in the unmanaged infrastructure scenario, it's completely the responsibility of the user to handle the infrastructure. So that means the user has to prepare the networks, the user has to somehow prepare the machines. And if they want to get rid of it at some point in time, of course, there's no knowledge in Gardener or Garden ADM what was done before, so the user has to do it. The user has to tear down the machines, delete the network configuration, and so on. The managed scenario, this is handled by Gardener. So with the Garden ADM Bootstrap, we use the Gardener extensions, we use Machine Controller Manager. They are preparing all this, and they can also be used to tear it down again. Hope this answers it. Another question in the chat, is Garden Linux required as an operating system for the nodes? Actually not. So of course, Garden Linux is the preferred operating system for Gardener, but yeah, Garden is open source. There are many OS extensions, Ubuntu, Flatcar, whatnot. You can write your own, so it's not hard-coded in Garden, so to say. You could also use something else. And another one, qualification criteria for adding server hardware. I guess this is about sizing of the servers, right? And how big they are. So of course it depends. Like in cloud environments, you can use different machine types depending on what you want to deploy in the end. Of course, Gardener comes with some preload for the system components, managing components. We have not yet written this down, but once this gets closer to production, we will prepare a guide for it, of course.
Okay, thank you.
Yeah, with that, I would like to thank you, Raphael and Dominic, for this very interesting presentation, and would hand over to Keith for the sustainability talk.
Thanks.
Thank you.
Okay.
Bye.
Yeah, that's a heck of a presentation to follow, Dominic and Raphael. Good job. Thanks a lot. I'll try to keep up the enthusiasm and the interest of our audience here by introducing a little bit about what the T-Systems B7 Sustainable Orchestration workstream has been working on. Give me one quick moment in order to find which one to share here. Preparing my slides. I'm trying to share. Okay. Can you see my screen?
Yes, we can.
Okay, perfect. All right. So, ladies and gentlemen, thank you very much for the opportunity today to explain a little bit about, again, like what the T-Systems Sustainable Orchestration workstream has been working on. My name is Keith Makta. I am the workstream responsible for T-Systems. And yeah, let's go ahead and get started. So, sustainable orchestration. I don't. Hold on. Come on, guys. Okay. So first, let me explain a little bit a topic that I'm sure most of you are familiar with already, which is the urgency of sustainability. So everyone knows about the AI and the GPU and the learning and the large language model training. All of this is dramatically increasing the amount of energy draw that's needed in the data centers. And this has brought us to the point, and we can see in the very near future, it will continue to bring us to points to where, you know, sustainable energy strategies and plans are absolutely needed in order to continue supporting the demand and growth of energy that's necessary. The innovation is what is really needed in sustainability at the moment. We need to figure out new ways to introduce sustainability in order to support advanced architectures and practices. There are multiple studies that show that this is necessary. And we can see in the most basic of graphs and forecast data coming in that data center consumption of the total electricity in the US is going to account for 13% by 2030. And in Europe, it's forecast to be between 4 and 5%. Edge data centers, where the edge continuum is going to play in the future, is already accounting for 10% of global data center load and consumption of electricity, and it's going to continue as it gets more and more popular and expands. The big problem also is that most companies do not know how to measure what their emissions and what their sustainability and what their efficiency ratings are at the moment, okay? And without understanding this, they also don't have an understanding of where it is and what things they need to look at in order to make themselves more sustainable. This means that they're unable to leverage cost efficiencies. They're unable to know exactly where and what they need to do in order to be more compliant with the upcoming regulatory requirements for consumption of sustainable energy within their operations. The B7 workstream, Sustainable Orchestration in the IPCEI program, is going to work to try to help address some of these issues. We were given the mandate within our workstream to define beyond state-of-the-art sustainability standards and practices. We were asked to find and figure out ways to do things better, perhaps using some things that are available today, but creating new beyond state-of-the-art practices in the areas of benchmarking and metrics, hardware level energy efficiency standards, and sustainable workload orchestration and management. The first thing that the workstream leadership did in alignment with a lot of people that are very smart here in T-Systems was to think about how we could take this this mandate and define some real tangible ways forward that would have a lot of value for the IPCEI program and the community as a whole. We wanted to make sure that anything that we defined in our work stream as being a target was obviously going to provide some value add in the sustainability realm. That what we defined was not just academic, but would be actionable and implementable, okay? That what we define and what we create would be platform agnostic, so it could run on the Gartner platform, it can run on the Open Telecom Cloud, it can run on the Orange platform, any of the partner platforms that will contribute later to the Edge Cloud Continuum. And we wanted to make sure that we used the open source tools to support digital sovereignty. And taking these things into consideration, we came to some of the most practical approaches. We chose to come to practical approaches that would be able to add value for the IPCEI program as a whole and all of its partners. So benchmarking and metrics, we came to the idea of something called sustainable evaluation, which will give visibility into the actual consumption patterns, as well as if optimized cost savings potentials of current edge service configurations. And it will also help to identify clearly where the inefficiencies are within the system, which components, systems, and configurations could use a configuration to bring them more into an established efficiency benchmarking. The next, for hardware level energy and efficiency standards, we worked on something called sustainable optimization. We took and across a very wide and far-ranging areas of types of hardware and configurations, we came to a comprehensive guide on how to tune edge infrastructure and hardware to optimize it the most for energy consumption. And then finally, we also, to address the sustainable workload orchestration and management objective, we came to the conclusion that a sustainable workload placement recommender would be a fantastic way to influence workload placements across cloud and edge infrastructures and platforms in order to help support the pursuit of cost reduction and energy or regulatory compliance objectives. Okay, a little bit more about each one of these. So sustainable evaluation and optimization, which is measuring, benchmarking, and optimizing the landscape for cost and efficiency. So what did we do here? Actually, what we've done with conjunction with the Fraunhofer Institute, the first thing that needed to be done was to create a benchmark, right? At the moment, there are lots of white papers, there are lots of studies, there are lots of things that talk about how in independent scenarios, how you can increase and how you can measure efficiency use of certain systems, but there was no framework of measurement and benchmarking, that was applicable across an entire edge cloud environment. And so we worked with the Fraunhofer to create the GMB-ECC, the Guided Measuring and Benchmarking of the Cloud Edge Cloud Continuum Standard. In this standard, it defines how to, for cloud services and edge services on the cloud, how to measure and benchmark efficiency. Then, on using this new standard, we implemented an open source benchmarking tool framework. So we built a tool that uses state representation as weighted models, so accounting for measurement variance. If you're not able to measure every single component within the edge service, the fitness adjustment, so we're able to define what the model complexity and granularity is. So how many components do you want to contain? What are the relationships? It also does the energy efficiency analysis. So there is error consideration. There's individual component analysis. So each of the components that are identified within an edge service are individually analyzed. And then it shows simplified graphing in order to be able to see overall what the edge service efficiency rating is. And then finally, using the standard methodology defined within the GMB-ECC, the tool will then measure and create a report that shows, based on the acceptable thresholds, what is the rating of the service efficiency as compared to a benchmark. Okay, and then finally, because it knows about price, it knows about efficiency, it knows about consumption of electricity, it will then be able to provide information about where the potentials for optimization and a resulting savings for monetary savings of energy use could be located. A quick view of the framework itself. So this sustainable evaluation tool consists of multiple modules, and they are all shared in the GitHub for the IPCEI program, and they are available. Here's how it works. So our benchmarking and metrics tool works so it's like this, starting from the left. So you would be able to take the service component list, capture information about each of the edge services, the hardware information and specification, the connectivity information, and the relationship of how they are all working together. We would also take measurement data. So you run the service, you execute a load, and you would then make sure that you are able to capture the energy consumption of individual components. You feed this information into the benchmarking tool. The benchmarking tool consists of two parts. So the optimum configuration and the optimum configuration evaluator is what is using the GMB-ECC standards. It considers what hardware you have, what's the connectivity information. It then calculates against the benchmark and then comes out with it also creates archetypes. Archetypes are application profiles. So your service may meet a web service profile. It might meet a database service profile. It might meet any type of profile. The benchmarking tool will categorize what type of service it is. This service is then managed and measured against the benchmark, and then the result of how it compares to the benchmark is displayed. The consumption analysis, however, takes the consumption data. We have all of the individual service components. We have the energy draw that they take during the loaded part of their service execution. It will then take and create reports and show you information about what was the cost of running the service, what's the CO2 footprint that comes out of running this edge service. It shows you the processor energy consumption, so CPU utilization, and it also will create an executive summary report which goes into more detail about the individual components and where they are in terms of overall service efficiency. So that's how the benchmarking tool works. Okay. Next, we talk about the sustainable optimization. Okay, so now we want to figure out and provide ways and means on how to make your service configurations more energy efficient and optimized. Okay, so for this, we created an optimization catalog. And the optimization catalog has multiple domains or areas where optimizations are focused. So it's focused on infrastructure and hardware optimization, software and services, network and communication, edge deployment, and planning for efficiency. So before you've deployed anything, you can refer to the optimization catalog and find out where you should look for efficiencies as you're starting to design your environment or your service. There are 15 different archetypes, which are the application type of profiles, and over 100 plus measures of optimization that can be applied. The optimization catalog addresses several of what we foresaw as edge cloud continuum challenges, such as system heterogeneity and complexity. Making some optimizations might have an influence on performance, so we take into consideration this trade-off. Energy is also used in the transmission of data, okay, back and forth between different nodes and different parts of the service. This is taken into consideration. Monitoring and scalability, we want to make sure that what we do and what we offer as recommendations are also applicable within this environment. And of course, environmental variability. Some systems are larger, some systems are smaller, some move lots of data, some move a little bit of data. So there is a consideration for these types of environmental variations within the optimization catalog. We took holistic measurement approaches. We think about task offloading, separating nodes into smaller ones in order to use and be more energy efficient. There's the key objectives of the optimization catalog is to provide methods and suggestions on how to reduce the total energy consumption while maintaining the quality of service with having an overall increase of sustainability, and where real-time adaptation is possible, this would be also included within the optimizations. The sustainable optimization works in conjunction with the benchmarking and sustainable evaluation tool. So the idea is that it becomes an iterative process. So again, starting on the left, you run the sustainable evaluation benchmarking tool, okay, which gives you results. Assuming that you have plenty of room for improvement within the benchmarking, you would then be able to refer to the optimization catalog, okay, and identify based on the archetypes that come out of the benchmarking tool a list of optimization measures. These optimization measures can then be identified, collected. They would be planned and designed and then implemented within the environment. and then you benchmark again and you reiterate. Okay, and you go through multiple iterations in order to come to a state in which your overall service is running within a benchmark acceptable threshold. And this is how optimization and the sustainable evaluation work together to provide insights and guidance on how to configure or reconfigure services to become as edge efficient and energy efficient as possible within an edge environment. Okay, next is the topic of sustainable workload placement. So the workload placement, our outcome here is that we've created also an open source workload placement recommender framework. The recommender framework takes into consideration lots of different information, and it's processed by 4 modules within the framework. The first is a workload fingerprinting agent. It's an AI large language model based. It basically takes information that it's fed and it's used to create unique workload fingerprints. These workload fingerprints are then evaluated by a module, resource time and energy prediction module, which is machine learning based. These fingerprints are pulled into the machine learning database, and then over time, it gets smarter and smarter about being able to forecast what the resource consumption would be, how much energy is expected to be consumed by the workload, and how long the workload runtime would be. Additionally, the framework provides a module for energy pricing agent. So it goes out to the internet and it brings in energy pricing and energy zone information, which it caches. And all of these modules then feed information into our sustainable recommender agent part of the framework, which is again a large language model. It consumes all of the outputs from the former 3 modules, and it derives the optimal workload placement, where the workload should go, which edge compute location, okay, would it be best served to run to maximize the cost efficiency of that workload. And a little bit more about how this works. So the framework details are: information comes in to the framework and to the different agents. We have information such as the workload definition, so the compute requirements and container size specifications. We have data center information such as what's the energy mix of the data center, the compute location, what's its geolocation, and what's its renewable energy percentage. Then we have metadata about the workload, which is basically at this point just the description. And we have the energy zone day ahead pricing. All of this comes into the recommender framework and is processed by the agents and is used and consumed by the sustainable recommender in order to output to any external system that is ready to receive it, information about where the workload should go, information, it does efficiency scorings, it does how long it estimates that the job or the workload is going to run. It will give a power consumption estimation, and it will at the end give even a recommendation to the orchestration broker what size container might be needed to be spun up in order to support the workload, such as the number of cores, how much memory, storage, so forth and so on. This information is then outputted to the orchestrator or to a further AI recommender in the background, which takes not only the sustainable recommendation for where the workload should go, but there could also be, and most likely will be, other recommendations such as policy-based recommendations and other types of influences that in the end will determine where the workload should be spun up. To give a bit more information about where our recommender should reside within an architecture of a cloud environment and the orchestrator. So here's where we sit. So we're getting information from the external providers. We're getting information from the asset manager, whatever this source is. And we're receiving this information. We're doing our recommendation here in the middle. Our recommender, as I mentioned a moment ago, lives amongst others, which would then feed information to the orchestrator, the scheduler and the orchestrator, who is then responsible for the actual orchestration of the Kubernetes cluster on whichever cluster and node that it decides that it should run on. But it gets our placement recommendation for the most sustainable. Okay, that was a lot, and we would like to build on that in 2026. So delivering additional sustainability value for the IPCEI program and all of its partners. One area is a new one called dynamic energy management. This is still in the definition phase, but the idea behind this is that we'll work with the Fraunhofer Institute again to, in a tagline, overcome other side of the meter blindness. What does this mean? We have the orchestrator already, or the recommender already, which is going to recommend moving a workload to, to another edge node where the compute could be run most sustainably. However, this dynamic energy management, it's going to extend that a bit and start talking about how we can bring energy to where the workloads need to run. So it could be that using next day pricing scenarios, we're able to connect ICT consumers, okay, so data centers, with energy aggregators to simplify and expedite the process of saying we can have daily contracts for electricity, to talk about how the sustainable surplus of energy on a super sunny day, to make sure that the sustainable energy is contracted onto the grid in order for it to be used in a higher percentage than it is today, because it's more visible, it's contracted, it makes more financial and commercial sense for the energy producers to participate in a new framework, which will allow them to not ground their energy that they've produced because they can't put it on the grid, but yet have a way to be able to sell it and utilize it. So this is sort of the idea behind becoming more visible in terms of energy planning as well as energy consumption forecasting in a very large and comprehensive fashion, far more than it is today. So this is how we're thinking about dynamic energy management. And we would also like to extend our AI recommender with a bit more information, which would make it more finite and have more fidelity in its recommendations. We're assuming and counting on the edge cloud continuum to bring more and more participants, so more and more nodes into the cloud environment and the compute availability landscape. And with this, we would like to leverage it by adding more information and inputs to our recommender agent. Adding what data center availability, adding more workload metadata, such as what's its default location, what's the closest location to the trigger, is there a latency tolerance that needs to be considered in terms of the workload? We would like to, in purple in the bottom here, add entire new categories of data, such as I mentioned, the dynamic energy management. We still need to define which pieces of information would fit most practically into the recommender in this context. We'd like to get data weather information. So obviously, if we know what the current weather is and what the forecasted weather would be for a certain location, we'll have better visibility in our recommendations on how to provide future scheduled job placements, not just, you know, at the moment type of job spin-ups. And this is what we would like to work on in 2026 for the recommender output. And we would also like to, for the benefit of the IPCEI and all of the partners that may want to integrate our recommender within their own landscapes, we would like to bring its architecture a bit more into a mature state. We would like to use microservices and build it more as a packaged solution with individual components that are working together. This will help with the operations management of it moving forward. And it will also, allow it to be incrementally improved and enhanced moving forward. You know, in a smaller risk state by working on individual components rather than messing with the thing as one big whole. That is, I think, the end of my presentation. I don't have much else to share of what we've been doing and what we would like to do. So I will end it here and say thank you all very much and open the round to any questions that there may be. Okay, I need to switch to chat real quick. So, Alex, is there a plan in the context of multi-cluster, also edge deployments in regards to workload placement recommendation to consider energy efficiency, cost and sustainability labeling of clusters and their nodes? We will consider anything. So if the platform can provide to us more metadata about a workload or about a cluster, then we can certainly ingest this information and use it as part of the AI output for its recommendation. If there is a, you know, if there's a standardized labeling that says that this cluster has these types of resources in it, and it has a benchmark efficiency configuration of 5 versus another one that has a benchmarking efficiency of 8, for example, and we see that the cost of doing business would be the same, yes, we would then recommend 8 if this information comes towards us. Does that answer the question? Perfect.
Keith, this is Vasu. Thank you for this wonderful insight. I have a couple of questions. Maybe I'll start with the GMB ECC benchmarking thingy. Is that something you want to expose to the end user? And I have a particular question why I'm thinking about this. So in the stack, if you come to a suggestion that you say, all right, there's some service, a database or whatnot, that would improve energy-wise from moving from Intel to ARM or something like that. You can make that suggestion internally, and when you own the stack, you can basically do this replatforming, if I may say, right? But for the end user, and then you optimize your internal services, that's fully understood. But for an end user who basically uses, let's say, the infrastructure or the services for deploying off-the-shelf software, does he also get this metric? And you know,
the standard is publicly published, so it's available for everybody. This is not something, you know, proprietary, or we have no IP on it. It has been released for everyone to use. It's generally, I mean, would an end user use it? I don't think it's going to be applicable for an end user who's more in an IIS scenario and wants to install software on it. I think it's going to be the responsibility more of the cloud provider and the platform provider to use it to ensure that what they're offering to the end consumers is as efficient as possible.
Okay, got it. Maybe you can add some links into. I looked in the presentation for links for more documentation. That would be great. And then So I figured that the end user kind of, it's more a cloud provider tool set. But then I have a follow-up question. How do you deal with the moral hazard? Because now you've bought, let's follow this, my example, you've got these Intel or whatnot servers, which are high energy consuming, and then you have newer ARM servers, and then you move internally, you move all these things to ARM or energy cheaper, let's say. And then obviously you still have to pay off the CapEx, right? So all of a sudden, from a moral perspective, you kind of make the more energy consuming service more cheaper, right, to the end consumer. Are there any thoughts of those, or?
I mean, no, I don't have a good answer for you there. I mean, obviously.
Okay. No, perfectly fair. Yeah, we're attacking with the same question, right? Okay. And the second part of the open source workload placement recommender, is there also a link for that? Can we test it? Can we work with you? Can I point some teams to you and then we'll test it out? Because it looks like you're also using all the same Kubernetes language. We are speaking the lingua franca, so we should be able to join hands there.
I absolutely welcome partnership on this. We would be more than happy to work with you and your teams to deploy this within your environment and create proof of concepts and figure out ways to interact with your orchestrator. So it's no problem whatsoever. Please, I don't have a link to send you right now, but you have my contact information.
I forwarded that. Yeah.
Well,
okay.
Oh, yeah. Let's get in touch, and for sure, I can put you in touch with my architects, and we can figure out a way how to collaborate on this. For sure.
Any chance that this open source project will also be donated to the Neonefos organization?
I'm very sorry. I didn't say this at the very beginning. Everything that we have done is. Let me go back here. Please. Everything that we have done has been published or will be published. So we are taking, the public funds from IPCEI, and we're developing everything in open source, and we're making it all available, freely available. So, our objective, was to provide value for everyone. And the IPCEI program can decide, how they want to distribute it. My understanding is it's an open source project, right? So all of the different companies and partners that are involved in it all have the right to use anything that any of us within the IPCEI program develop. So it will be published. I can't tell you if it's on our GitHub already. And I'm pretty sure I can't tell you the answer if it's already been shared on the IPCEI Git or not, but it will be made publicly available for everyone.
Perfect. Thank you. And that's good to hear. Yeah.
Thanks.
100%, Any other questions?
Okay. Yeah, that I wanted to ask as well. Last chance for questions.
Thank you. My name's Mirs. Just a quick question. You talked about these energy aggregators. Could you maybe elaborate a little bit more? I know you said it's still in the definition phase, but I was wondering if it's similar to what they're also doing in the United States, where they also include in energy aggregators, they also can include community solars, and if that's what's also being considered here as well.
Be honest with you, this vision is not mine. This came from a colleague. And I'm still trying to wrap my brain around it. But what we have done is we have already done a pre-qualification with the Fraunhofer. We sat with them and he sat with them and discussed the ideas. And they say, there's really something here, and we'd like to expand our look and research into it. The idea in general, I don't know what the US is doing. So I can't say if it's the same or something different or better. But what I can just elaborate is it's in general, the vision is about making sure that surplus energy is visible to the consumers, and the demand, the forecasted demand of the consumers is visible to the energy producers. And when you can connect these two things together through a to be determined framework recommender system, you know, then you can become more efficient, because then you can make sure that no renewable energy is being grounded. And if you're using that, then you don't have to make as much dirty energy, you know? And so it has a sustainable component, and renewable energy costs less than generated energy. So, you know, this is also a cost potential here. And the idea, if I understand it, is to create the what's the right word in English? To create the incentive, you know, incentive for the energy aggregators to participate in this, you know, because if we can say, hey, we have this framework, and now, you know, we're getting forecasting, and do you want to sell energy, and getting them interested in becoming more partners, and telling us what are the edge locations or the solar or the wind locations where they have, you know, little compute centers that can be added to the edge cloud continuum node base, you know, where the future recommender might be able to decide to shift the workload if that's indeed the case, you know, and would be the best thing for it to do. And where the aggregator or the energy producer would then say, hey, you know what, I'm not going to lock you into a 1-year contract for a certain price data center. You know, we can build up a framework of a 24 or 48-hour contract basis, you know, where, you know, based on a forecast and power generation forecasting and so forth, you can get more dynamic in your contracting, which has, again, the incentive for the consumers to be involved on that side, and it has cost savings, and it's using more renewable energy. So I know it's quite vague and nebulous what I just said, I admit that, but there's something there, right? And what we want to do, and what the sustainable orchestration's mandate is to find new, beyond, you know, state-of-the-art ways of being more sustainable. And this has some value in doing more research and development, and figuring out how we can bring something tangible and advantageous to the IPCEI program and to the benefit of all the participants of it.
Thanks, Keith.
Thank you for the question.
Okay, there was one last question coming up, Keith, about if you can share that with the Workstream 2.
Yeah, I will make sure that the whole presentation is available. Yeah, for sure.
Okay, good. So with that, I would like to close. Thanks a lot again to Dominic, Raphael, and Keith for the two very important and very interesting talks. And looking forward to the next meeting in a month from now. So everybody, see you. I will publish the recordings in all the known places so that you can access them afterwards as well. See you. Have a good day. Bye-bye.
Thank you very much.
Bye.
Thank you.
See you, bye.
Yeah, and I'll send you the presentation in a mail in just a few minutes.